Hello everyone. Continuing with organic chemistry, I'm going to discuss one of the first chemical reactions that I'll do in module 4 is free radical substitution. It's not exactly the simplest of all the chemical reactions in module 4, the beginning of organic chemistry and organic synthesis, but I think it is essential that you learn free radical substitution first, because in learning free radical substitution, you actually learn how to introduce a functional group onto a hydrocarbon, a saturated hydrocarbon, such as alkanes. And the importance of introduction of a functional group to such molecules enables you to then proceed to change that functional group to some other functional groups, and ultimately proceed to make the desired product. So why is it called free radical or sometimes radical substitution? Well, it's because free radicals are involved. So what are they? When you have a hydrocarbon, such as, for example, I don't know, ethane. You know, methane and ethane, natural gases, propane and butane, petroleum gases, and you really associate alkanes, generally speaking, or most of them, with fuels. Things that have taken millions of years, billions of years to be produced, we just burn them for fuel. Can we do something else with them? Yes, we can. But then not as they are. Perhaps we need to change them to something else slightly more useful. So basically the reaction is that if you have an alkane, you can react it with, for example, halogen, such as chlorine gas, for example, and then you can turn it into, say, chloroethane plus HCl. Chloroethane. Now this is far more useful than that. Not because it's chloroethane, but what is it that you can do with chloroethane to convert it to some other products as well? Now we can do this reaction by what is known as free radical substitution. And we do need a reaction condition UV light. Now what is the role of UV light? So if that is the equation, what actually happens? These reactions occur in 3 different steps, and you are required to know these steps and what is entailed in each of these steps. Step 1 is called initiation. How the whole thing initiates. So now in initiation, you get your chlorine. Now I'm going to show the bond between the chlorine molecules. And with the help of UV light, so UV light provides the energy to actually break these bonds apart. So one electron goes and sits over there, the other one goes and sits over there. Basically what we get is the original chlorine atoms that we had before. You see, chlorine halogens, 7 electrons in the outer shell, extremely reactive. So what do? They come and share electrons and form a diatomic chlorine molecule, which is relatively stable. So with the help of UV light, we provide the appropriate energy to actually break the bond apart and basically turn them to what they were originally. And we turn them to you and me, 2 chlorine atoms, so 2 chlorine radicals. And sometimes they put a dot there just to show that there are free radicals. Now this step is initiation. These one-sided arrows, before I proceed, are referred to as homolytic fission. Heterolytic fission is when both the electrons go from one side to the other and results in formation of ions. You see, when 2 species are sharing 2 electrons, which makes a bond, if both of them go to the other side, this one takes its electrons as well as another electron, so it becomes negatively charged. And this one that has been stripped of that electron, its own electron, turns into a positive charge. But what if they have equal sharing of electrons? They just get their own electron back. They don't turn to ions. They just get their own electron back. and they turn into free radicals. Now, these guys are extremely reactive, and they react with anything in order to reestablish the stability that they once had. How do they do that? By reacting with things. What do they react with things? In this case, well, let's say you've got chlorine, you've got ethane in a reaction chamber, which is enclosed, and through a window, somebody comes along and flashes a UV light. The second stage is called propagation. To propagate means to make more. Propagation. Some of you have heard this maybe in biology as well, to make more of the same thing. Now, propagation is in two steps. Step one, yes, let's use that example. So CH3, let's write a displayed formula, because every time you want to show a reaction mechanism, you have to show a displayed formula. You have to show how bonds break or form. So this chlorine free radical that came along there comes along and say, hey hydrogen, come and react with me. Hydrogen has 2 electrons, isn't it, between carbon and hydrogen. So instead of now sharing that electron with chlorine, it shares that electron with carbon, it shares it with chlorine. And then the other electron goes and sits on the carbon. So what is the result of that? So you have CH3, CH2 dot, because now this bit has turned into a free radical, plus HCl. Right? Now let's go to the next page so that I can show you the second stage. Of course, anytime you wish to see other things, you can always pause and go back and watch. That's the advantage of having these video clips. You can always pause, give yourself more time, go back, revisit. So what happens now? In the second stage of propagation, you have CH3, CH2 dot on the carbon, right? Now this goes and finds a normal diatomic chlorine molecule in the reaction chamber, and then it reacts with that one. So it's going to pinch that chlorine there, and then the other chlorine turns into a free radical as well. So ultimately, what do we get? We get the intended product, CH3, CH2Cl, which is now chloroethane, plus a chlorine free radical is now again regenerated. So this can go back, find another ethane molecule, and carry on doing what it does in the process. That's why this process is called propagation, because you keep going. I mean, what stops propagation, or in essence, what stops a chemical reaction is, well, when you run out of reaction reagents in the chamber, or what is known as step 3, which is termination. Well, in termination, it's quite clear that how do these reactions get terminated? One way that they can terminate it is that instead of free radicals going and reacting with other molecules, like in this case, ethyl free radical reacting with chlorine, or chlorine, or chlorine free radical reacting with ethane, they actually react with one another. In what way? So, for example, there are always three examples, or 3 ways in which this termination can occur. If, for example, 2 chlorine free radicals come together, and instead of going and reacting with other things in the reaction chamber, they actually react with one another and turn into chlorine gas. Or a chlorine free radical, in this particular example that I've given you, reacts with ethyl free radical. So they come together, they produce CH3, CH2Cl, which in fact is the intended product in this case, but then in doing so, they do not regenerate a free radical. So the reaction stops. And then the third scenario, which might surprise some people, is when in this particular case, for example, two ethyl free radicals come and react with one another. And then you end up with butane, CH3, CH2, twice, CH3. Now some people might be thinking, how did butane get into the reaction chamber? Have I had impurities? No, it's as a consequence of termination process. In the exam, usually, I mean, seldom they ask you to write all three examples, because if they, all possibilities of termination, because if they do, then they have to give you a lot of marks. So what they usually do is they ask you to give an example of termination. And you can choose any of these things. I usually go for the one which is the easiest, the fastest to write. I suppose the only step that might challenge you a bit and you need a bit of practice on it is the propagation step. All of these steps actually make sense. The names, I mean, initiation, unless you have, in this case, a halogen free radical, how can the reaction start? It doesn't. And then in propagation, you have to show in steps as to how the intended product is made, and it's allowed to continue. So for example, in the second step, you can quite easily see that the intended product is made, but results in formation of a chlorine-free radical, and which will carry on, is allowed to carry on the reaction. So things that you also need to take note of, like I've mentioned, is that homolytic fission. So when you have a bond and a bond opens up, and each of these guys will get equal sharing of electrons. All right, so each of them get one electron each on either side, as compared to heterolytic fission, which we shall discuss in the next lesson, where movement of a pair of electrons is shown by a double-sided arrow. A one-sided arrow represents movement of one electron, and as far as your syllabus is concerned, this is the only time that you'll actually see it in reaction mechanisms, in free radical substitution. In all other reactions that I will show you next is there are double-sided arrows and there are heterolytic fission, which means the movement of a pair of electrons. Okay? I think if we keep this as it is, so you can concentrate on one reaction at a time and learn that and learn it well, we don't need to make the video clip any longer than this. All right? Go back a couple of times, back and forth, so that you understand all the steps and practice questions, etc., etc. But the procedure is as you just saw. Okay? All right, thank you.